Night over Australia's Outback. Stars hiss with heat, and a radio tower cuts a black line against the sky. On a quiet frequency, a faint periodic pulse appears. Steady, uncanny, and impossible to ignore. First logged after midnight, local time, at a small roadside research station, hundreds of kilometers from any city, the signal rides the noise floor, then ticks and returns. On waterfall plots and oscilloscopes, it's a narrow tone with a clean rise, brief plateau, and soft decay. Not strong, just disciplined. It repeats. Heat haze shimmers over red earth. Far above, the ionosphere bends radio like glass, layered, moving, alive. Propagation can turn distant transmitters into local ghosts. In the field, scientists angle Yagi antennas and loop coils from a dusty 404. A portable SDR hums. Laptops scroll live spectrograms in the dark. They log UTC timestamps, bearings, noise levels, and drift. No transmissions, only listening on public roads and permitted sites. Hypotheses stack up. Distant HF skywave, a drifting low Earth satellite beacon, aircraft telemetry, or a ground source, pumps, fences, power lines, riding the air. No conspiracies here, just a curious signal and careful method. Extraordinary claims require ordinary discipline: measure, repeat, compare. The pattern is the clue: a pulse every few seconds, minor frequency wander with temperature, and occasional fades that match changing skip conditions. If it's local, bearings should converge. If it's distant, polarization and timing may betray a path through the ionosphere or a satellite arc. Coordination matters. Logs and audio are shared with colleagues and regulators. Do not transmit without a license. Do not trespass. Safety and law first. Out here, lightning crawls on the horizon and dust devils twist across saltbush flats. The spectrum crackles with nature and machines. Signals layered like weather. Through the small hours, the pulse keeps time. Sometimes it brightens, sometimes it sinks, never quite gone. Bearings are drawn on the map. Two lines cross near a remote track. Another pass shifts the intersection, hinting at motion or sky bounce. Why does it captivate? Because mystery is the spark. Method is the path. Each clean observation narrows the field, turning rumor into evidence. Respect the land, the rules, and the spectrum. Work from public roads and permitted pullouts. Leave only tire tracks and better data. And at dawn, the desert breathes. The pulse thins, then slips beneath the noise, leaving questions, coordinates, and a trail to follow when night returns. Across Australia's interior, radios hear more than voices. A faint carrier rises at dusk, fades by midnight, and whispers back before dawn. A pattern that hints at physics, not folklore. In this chapter, we break the puzzle down like investigators do. Start with the band, note the modulation, log the timing, and line up the usual suspects: ionospheric skip, tropospheric ducting, satellites and space debris, aviation beacons, industrial telemetry from mines and pipelines, plus nature's own radio, spherics and whistlers. No verdict, only possibilities weighed by evidence. First triage, frequency. LF and MF often carry ground waves and lightning noise. HF can leap across horizons via the ionosphere. VHF and UHF are mostly line of sight but can bend in special weather. Microwave links are pencil thin. Next, modulation: AM, FM, SSB, digital bursts, wideband noise, or narrow beacons. Finally, timing: diurnal swings, weekly maintenance windows, or satellite pass schedules. Plot these three and many culprits fall away quickly. Ionospheric skip can bounce HF signals hundreds or thousands of kilometers. Near sunset and sunrise, changing F-layer density shifts, which bands open or close. A distant AM or digital HF channel can fade, flutter, then surge as layers refract differently. If the mystery lives on HF and follows solar and dusk patterns, skip rises on the list, especially during high solar activity. Tropospheric ducting is a VHF and UHF trick. Over salt lakes or hot plains, temperature inversions can trap radio waves in low-level layers, guiding them far beyond normal range. Dust storms and shimmering mirage conditions often flag these inversions. If a VHF carrier appears only on still hot nights and vanishes when the air mixes, a duct could be the conduit. Satellites add another path. Low Earth orbiters sweep overhead in minutes, often with a telltale Doppler shift and repeating pastimes. Navigation constellations sit higher with stable carriers, while weather and comsats operate at fixed slots. Match frequency plans and pass predictions. If the tone slides steadily in pitch on each pass, orbital origins are plausible. Aviation beacons and communications concede confusion. VHF AM traffic clusters near airports and routes. ADS-B at 1090 MHz is pulsed and data-rich. Legacy NDBs and newer nav aids have distinct tones. Cross-check NOTAMs, flight tracks, and beacon registries. If signals spike with overflights or align with aerodrome hours, aircraft systems may explain them. Mining operations saturate remote bands. Haul trucks, dispatch repeaters, microwave backhauls, and telemetry for pits and conveyors run day and night. Repeater towers on ridgelines and dish links between camps can leak test tones or control bursts. If the signal clusters near leases and mirrors shift changes, industry is a strong candidate. Pipelines thread the interior with SCADA links and cathodic protection monitors. These systems often emit scheduled, short telemetry bursts, sometimes narrowband FSK or PSK, with regular duty cycles. If logs show neat, repeating intervals independent of weather and daylight, pipeline telemetry or utility control becomes likely. Infrastructure can masquerade as mystery. Weather radar chirps, microwave relays, wind farm maintenance channels, even poorly shielded electronics can raise local noise floors. Ferret chokes and filters tame some of it. Spectrum hygiene surveys help separate site noise from true distant signals. Nature speaks too. Spherics, broadband cracks from lightning, skip for thousands of kilometers, while whistlers slide in frequency along Earth's magnetic field lines. On spectrograms, they paint distinctive streaks and slopes. If bursts align with distant storm maps or display descending tones, natural radio may be the simplest answer. Investigators map reception reports across central and western Australia, layering terrain, lakes, and weather. Patterns emerge. Ducks along salt pans, stronger hits near ridgelines, nulls behind mesas. Combining bearings from multiple stations tightens the search without stepping foot off-road. In the lab, software-defined radios and filters do the fine work. Isolate the carrier, inspect sidebands, and watch the waterfall for drift. Bandpass filters, clean coax, and ferret on every lead keep the bench honest. Modulation analysis, AM depth, FM deviation, symbol rates, often narrows a candidate list to a handful. Scheduling adds clues. Satellite passes repeat predictably. Maintenance windows hit the same clock. Shift changes echo through dispatch nets. When logs align with orbital predictions or roster times, cause and effect sharpen, though proof still demands caution. Ruling out suspects is as valuable as finding one. If there's no Doppler, LEOs drop in rank. If only night openings appear on VHF, tropospheric ducts rise. If the tone survives storms without lightning signatures, spherics fall away. Step by step, the possibility space shrinks. All of this happens within rules and respect. Licensed bands, site permits, and safety first in remote country. Good records, shared data, and transparent methods keep the work reproducible and careful. Science before certainty. Where does that leave the mystery? Plausible, testable paths remain. Ionospheric skip, tropospheric ducting, satellite spillover, aviation beacons, mining or pipeline telemetry, and natural radio from distant storms. The checklist stays open. Evidence first, conclusions last. Night on the Tasman. Amateur radio operators begin comparing notes. Strange bursts after dusk. Faint but consistent. Call signs anonymized, frequencies noted, recordings saved in UTC. A quiet mystery asks to be mapped. Logs tighten the timeline. Operators record burst times in UTC, capture audio and waterfall screenshots, and share bearing estimates. A shared spreadsheet grows, columns for frequency, SNR, azimuth, and location. A plan forms, triangulation. Print maps, mark waypoints, align compass bearings from home stations. The first confidence polygon appears, broad, but a start. Mobile direction finding begins. A rooftop loop and a small Yagi sweep from public roads with check-ins on simplex, headsets on, call signs blurred, every stop logged with GPS. At each vantage, a handheld spectrum analyzer sweeps the band. Peaks tagged, azimuth written, noise sources noted, bearings converge by degrees, ethics and safety lead. No trespass, public road vantage only. High-vis vests, hazard lights, radios monitored, permits and regulator contacts in place before any tests. Back at base, bearings draw triangles on a digital map. Each new line tightens the solution. Confidence ellipses shrink as the dataset grows. A breakthrough. The spectrogram shows a repeating burst every few minutes shortly after sunset. Overlays of clock and temperature suggest a link to evening inversions or scheduled telemetry. Hypotheses stack, ducted propagation on an inversion layer, a timer-driven sensor, or maintenance telemetry. The team drafts controlled tests and comparison sites. Second night, repeatable window confirmed at multiple waypoints. UTC stamps, SNR, and antenna headings align. Interference checks pass. Coordination follows. Regulators receive a concise report and raw logs. Stakeholders briefed. No raw coordinates shared publicly until source is verified and impacts understood. GPS tracks trace careful loops along public routes. Updated waypoints nudge the polygon toward a narrow corridor, likely along existing infrastructure. The aim is respectful: locate, document, and if needed, help mitigate, without disruption. Next steps await daylight, permits, and the right people on site. Community science works when careful. Logs, bearings, and patience turn noise into a signal. At dawn, the checklist is clear: verify, contact, collaborate. Sunrise over the mast, a new day, a tighter circle, and a plan built on ethics, permits, and shared curiosity. First, the basics: license, safety, respect. If you listen for unusual radio signals in Australia, start with the rules and a plan. Check your license status and ACMA regulations. Know what bands and power levels apply, and never transmit unlawfully. Listen legally. Use approved receivers and antennas. Avoid interfering with emergency, aviation, and maritime services. Travel smart. Tell someone your plan. Carry water, sun protection, a PLB, and vehicle spares. Then turn back early if weather shifts. Where to set up? Public sites with clear horizons. Never on closed country, private land, or near sensitive services. Respect country. Heed ranger signage. On indigenous lands, obtain permissions. Some places are culturally restricted or sacred. Leave no trace. Pack out everything, protect vegetation, and keep antennas away from wildlife and pathways. Setup is simple: portable SDR or scanner, telescopic or small loop antenna, headphones, and a notebook or logging app. For each signal, press record and note the details as you listen. Log format. Keep it clean and consistent. Record frequency to the hertz if possible, mode and bandwidth, UTC time, GPS location, your receiver and antenna, plus a brief description. Add proof: short audio clip and a screenshot of the waterfall or spectrum view showing the signal. If it may involve safety or interference, report promptly and accurately. Do not chase or probe the source. Share responsibly with local radio clubs and researchers. Keep coordinates general if a site is sensitive. Curiosity first, caution always. Good notes turn mystery into useful data, and let the sky remind you why it matters. Mystery is a path to stewardship.